everyone. In the previous class, we started our discussion on elastic stress distribution around circular tunnels, and I told you that what is the geometry of the problem, what are the loading conditions, material properties and the boundary conditions. And then we started deriving using the Airy's stress function approach, and we were in the middle of the application of the boundary conditions. We already applied the boundary conditions at r tending to infinity. So, let us continue from the previous class. We have two more boundary conditions which is at r equal to a, that is the radius of the tunnel. So, what happens when we excavate? There is the stress free boundary. So, at the periphery of the tunnel, that is at r equal to a, there will not be any stresses. So, therefore, the radial stress as well as the shear stress is going to be equal to 0. So, let us apply that and then try to get the expression for various stress components. So, here in the previous class we applied the boundary conditions at r when it was tending to infinity. So, we have now that is at r equal to a, we have the stress free boundary, that is sigma r is equal to 0 and tau r theta is also equal to 0. So, let us apply to this, that is sigma r to be equal to 0. So, we have half Sx plus Sy plus half Sx minus Sy cos of 2 theta. This is going to be equal to sigma r, which is equal to 0, and this in turn in terms of the stress function phi we can write as a upon small a square, although we will have a by r square, but here we are applying the condition at r equal to a. So, I will just substitute r to be equal to a here plus 2b plus minus 2c minus 6e a to the power minus 4 minus 4f a to the power minus 2 cos of 2 theta. Now, if you compare the terms, so comparing the terms on both sides of the equation, so what we will get is half Sx plus Sy is equal to a upon a square plus 2b, and of course, this is at r equal to a, and this is going to be equal to 0. This is going to be equation 10d. So, these equation numbers are in continuation with the previous class. So, then the other term is going to be minus 2c minus 6e a to the power minus 4 minus 4f a to the power minus 2. This is equal to half Sx minus Sy, this is equal to this, and this will also be equal to 0. So, individually both the terms have to be equal to 0 if this equation is to be satisfied. So, I will write this as equation 10e. So, we have the another condition, that is tau r theta to be equal to 0. So, we do the similar exercise with reference to that. So, what we are going to get is half Sx minus Sy sine of 2 theta, that would be equal to 2c plus 6d a square minus 6e a to the power minus 4 minus 2f a to the power minus 2 sine 2 theta, and of course this is going to be equal to 0 because it is the stress free boundary. Now we have already seen that this d to be equal to 0 in the previous class. So if we just substitute it here, what we get is 2c minus 6e a to the power minus 4 minus 2f a to the power minus 2. This will be equal to 0, and I mark this equation as 10f. So here we have got the equations from 10a to 10f. So let us try to see that how we can determine the different boundary conditions here. So this equation 10a gave us that 2b equal to half Sx plus Sy. Then equation 10c gave us 2c equal to minus half Sx minus Sy. Then 10d was a upon a square plus 2b to be equal to 0, and from here you can determine the constant a in terms of the constant b, which you can obtain from here. So this is going to be minus 2b into a square, and then 2b here you just substitute this. So minus a square upon 2 Sx plus Sy. Then we have d equal to 0 already. Now if you add equation 10e and 10f together, or if you combine these together, see what will happen. So 10e was minus 2c minus 6e a to the power minus 4 minus 4f a to the power minus 2 equal to 0, and then you had 2c minus 6e a to the power minus 4 minus 2f a to the power minus 2 to be equal to 0. So just subtract it. So this will become minus, this is plus, and this will get cancelled. So this is going to be minus 4c minus 2f a to the power minus 2 to be equal to 0. And from here what we can get is 4c is equal to minus 2f a to the power minus 2, or you can write as minus 4c equal to 2f a to the power minus 2, or in other words we can write it as f equal to minus 2c upon a to the power minus 2. Or we can write, see 2c is this, so we can write this f to be equal to a square upon 2 Sx minus Sy. Just substitute 2c to be equal to minus half Sx minus Sy here in this expression, and this is what that you are going to get. Now from equation 10f, now what we have is minus half Sx minus Sy minus 6e a to the power minus 4 and then minus 2f a to the power minus 2. Okay, so this is going to be minus Sx minus Sy a square into a to the power minus 2. This is going to be equal to 0. So this and this will get cancel out, and from here what you are going to get as the expression for E as minus 1 upon 4 Sx minus Sy a to the power 4. So if you just take a look at this slide, you will get to know that we already have got A by this expression, then B by this expression, C by this expression, D is already equal to 0. Then we got E by this expression and F using this expression. So, this is how using the boundary conditions we could find all the arbitrary constants. So, now once I have the expression for all of these, I substitute it back and then try to get the expression for stresses. So, I just what I will do is I will mark this complete set as equation number 11. So, if I substitute this equation number 11 to earlier equations 9a, 9b and 9c, this is what that we are going to get as sigma r to be equal to minus a square upon r square into 2 sx plus sy plus half sx plus sy plus half sx minus sy plus 6 upon 4 sx minus sy a to the power 4 r to the power minus 4 minus 2 sx minus sy a square r to the power minus 2 into cos of 2 theta. Or what we are going to get is take common half sx plus sy. So, we are going to get 1 minus a square upon r square, and then here you take half sx minus sy common, and what you will get is 1 plus a to the power 4 upon r to the power 4 minus 4 a square upon r square into cos of 2 theta. I will mark this equation as equation 12a. Now, similarly, we can substitute this equation to the respective equation for sigma theta. So, I am going to get in this particular manner, that is a square upon 2 r square sx plus sy plus half sx plus sy plus minus half sx minus sy minus 6 upon 4 sx minus sy a to the power 4 r to the power minus 4 into cos of 2 theta. And what we get here is that if I take half sx plus sy common, so we get here as 1 plus a square upon r square minus half sx minus sy into 1 plus 3a to the power 4 upon r to the power 4 into cos of 2 theta. This will be equation number 12b. Now, we have another equation which is for tau r theta. So, let us do that as well. So, we have this tau r theta will be equal to minus half sx minus sy plus 6 upon 4 sx minus sy a to the power 4 r to the power minus 4 minus sx minus sy a square r to the power minus 2, and this whole in a box bracket and the multiplication by sine of 2 theta. Now, you take half sx minus sy and also the negative sign outside this bracket. So, you will end up having 1 minus 3a to the power 4 upon r to the power 4 plus 2a square upon r square into sine of 2 theta. Mark this equation as equation number 12c. Now, kindly note here that sigma r, sigma theta and these tau r theta, they all are the function of r theta a sx and sy only. What I mean here, that they are not the function of E and mu, that is the elastic modulus and Poisson's ratio of the rock. So, what does this mean? That whether these stresses are independent of the elastic properties of the medium, that is what it shows mathematically. But what happens is, it is not that these stresses are independent of the material properties, they come in picture in an indirect fashion. So, the strength of the material is defined in terms of QC, QT and tau. So, this QC is UCS, QT is the tensile strength and tau is the shear strength. So, how these really affect if it is not showing mathematically in the expression of sigma r, sigma theta and tau r theta. Let us see that the strength of the material, it degrades as the size of the cavity changes. These stresses are equated to the degraded strength and hence the elastic properties, they come into picture in an indirect manner. So, it is not that the stresses are not related to the elastic properties of the rock medium. Now, these equations 12a, 12b and 12c, they give us the stress components for the biaxial stress field, where the applied stress field at the infinity was taken as sigma x to be equal to Sx and sigma y to be equal to Sy. So, we have now the general form of the biaxial stress field. Let us try to understand in more detail that what happens in case if you have the uniaxial state of stress or the hydrostatic state of stress. So, these two state of stresses, they are going to be the particular cases of the general biaxial stress field. Take a look here first for the hydrostatic state of stress, that is in this case your Sx and Sy, they both will be equal, and when they are compressive, I will just put a negative sign with their magnitude, because if you recall in the previous class I mentioned to you that all these are generated with tension as positive. So, when it is compressive, there is going to be a negative sign associated with that. So, just substitute the values of Sx and Sy, which is equal to minus P in equation number 12, and you will get the state of stress for hydrostatic state of stress. So, you will have sigma r as minus P 1 minus a square upon r square, and if you just substitute sigma r, which is at r equal to a, that means just substitute r to be equal to a. So, this is what that you are going to get as 0. Then sigma theta will be minus p 1 plus a square upon r square, and if we want to find out sigma theta at r equal to a, what we have is minus 2 times the value of in situ stress, that is P. Now, tau r theta is going to be equal to 0 and tau r theta of course at r equal to a will be equal to 0. So, all these three equation, I mark it as equation number 13. Now, I define the stress concentration factor, which is sigma theta upon minus p. Now, basically this stress concentration factor, in general its definition is going to be any particular stress and its ratio with the in situ stress. So, that is P. So, let us say if I want to find out the stress concentration factor with respect to sigma r, so that is going to be sigma r upon P. So, in this case, this stress concentration factor with respect to sigma theta, this works out to be equal to 2. So, for the hydrostatic state of stress, see what happens at the tunnel periphery, sigma r equal to 0, tau r theta equal to 0, and the stress concentration factor sigma theta upon P with a negative sign of course is equal to 2. Now, coming to the uniaxial state of stress, so in this case I have the applied stress only in y direction and in x direction this is equal to 0. That means the stresses are applied only in the vertical direction. So, what is going to be the expression for sigma r, sigma theta and tau r theta? Just substitute these values in the equation 12. So, this is what that we are going to get, half Sy 1 minus a square upon r square minus half Sy 1 plus 3a to the power 4 upon r to the power 4 minus 4 a square upon r square into cos of 2 theta. Then we have sigma theta as half Sy 1 plus a square upon r square plus half Sy 1 plus 3 a to the power 4 by r to the power 4 cos of 2 theta, and tau r theta is going to be equal to half Sy 1 minus 3a to the power 4 upon r to the power 4 plus 2a square by r square into sine of 2 theta. So, this equation I call as equation number 14. Now, what will happen at r is equal to a, which is at the tunnel periphery, and theta to be equal to 0, that means along the x axis. So, here just substitute it. So, this first term will become equal to 0 and this cos 0 will be there. So, that will give me sigma r to be equal to 0 and your sigma theta will be equal to, just substitute. So, that is going to be half Sy into 2 plus half Sy. This is going to be you substitute r to be equal to a. So, this is going to be 4 and then cos of 2 theta, theta is equal to 0. So, we have here as 1. So, this is going to be equal to, so this is Sy and 2 Sy. So, this will become 3 Sy. Now, that is the first position, that where we want to find out sigma r, sigma theta. Then the second location is at r is equal to a and theta is equal to pi by 2. So, remember these were the axes, x and y axes, and we had the circular tunnel. So, this was any point here and this was represented by r comma theta. R was this distance and theta was this angle. So, when I say theta to be equal to 0, this means it is this location, and for theta equal to 90 degree, it is this location. So, this is typically crown of the tunnel. So, this just substitute the values, what you will get is again sigma r to be equal to 0 and sigma theta you will get as half sy into 2 plus half sy into 4 into minus 1, because here theta equal to 90 degree. So, you will have that as to be minus 1. So, this is going to be minus sy. So, in this case the stress concentration factor, which is sigma theta upon sy, that is equal to 3 for the first condition and minus 1 for the second condition. Now, note it that here it is minus and here this is positive only. So, what does this signify? So, for the uniaxial state of stress, which is represented by Sx equal to 0 and Sy non-zero, we saw that sigma theta upon Sy works out to be minus 1. So, if the applied stress is compressive in nature, the resulting tangential stress at the crown portion of the tunnel is going to be tensile in nature, because there is the change of the sign. So, if it is here positive, this is here negative. So, we need to be careful here that we have the tensile stresses in the crown portion of the tunnel. Now, the magnitude of this is equal to the applied stress in y direction, but then equal and opposite magnitude. If Sy is greater than sigma t, which is the tensile strength of the material, what will happen? This will result into the tensile failure of the rock in the crown portion of the tunnel, which is this position. This is y axis, x axis, and this is the crown position where theta equal to pi by 2. So, this becomes a critical condition. So, you should keep in mind that the uniaxial state of stress, in case if you have the tunnel subjected to only the vertical stresses, in that case in the crown portion of the tunnel there is going to be the presence of or the occurrence of tensile stresses, and that makes that portion very critical. If this stresses becomes higher than the tensile strength of the rock, and you know that the tensile strength of the rock is less than the uniaxial compressive strength. So, we need to be extremely careful that the applied stresses should not become more than the tensile strength of the material, and if it is becoming, that means the tensile failure is going to occur, and we need to be careful, especially here in the crown portion where such a condition can occur. Now, in case if you have the hydrostatic state of stress, resulting stresses both radial as well as the tangential stresses, we have seen that they were all compressive in nature. So, for the uniaxial state of stress, it is not only the stress concentration factor at the periphery of the tunnel is 3 times the applied stress, but due to the tensile stress condition in the crown portion, this uniaxial state of stress becomes most critical state of stress. Please keep this in mind. Now, when I say crown portion, means essentially I am referring to theta equal to pi by 2, and later on I will also use the term invert. So, invert of the tunnel corresponds to theta equal to minus pi by 2. Now, these expressions for these stresses which are given by equation number 12, they are independent of the elastic property, which were E and mu, this we saw earlier. So, this does not really mean that the stresses are going to be independent of the material behavior. What happens in practice, that when you increase the size of the excavation, the strength of the rock is influenced, and the mechanical properties such as its uniaxial compressive strength, tensile strength and the shear strength, they degrade. So, from the design point of view, these degraded values in the strength characteristics, these govern the design of excavation. So, indirectly that is how the properties, elastic properties, they come into picture. Now, let us take a look about the stress distribution. As of now, we have seen the various expression for uniaxial state of stress as well as hydrostatic state of stress. So, how this looks like, how its variation looks like with the increase in the distance from the periphery of the tunnel. So, we are going to discuss about that. So, normally at theta equal to 0, this means it is this axis that we are talking about. Normally at r by a, when it is very large, that means to the extent of 4 to 5, this sigma r becomes equal to 0. That is what that you see when I plot the variation of sigma r. So, you see normally at this, it is very small, negligible. For all practical purposes, we can consider this to be equal to 0. The tangential stress, which is the sigma theta, and the variation has been shown by this curve. At the vertical and at infinity, it must be equal to the applied stress, because that is what is the boundary condition is, and you see that this is what that we obtain from this figure, that when it goes beyond, so you see that here this stress concentration factor becomes equal to 1. So, this corresponds to stress concentration factor of 1. So, what does that mean? That the sigma theta is equal to Sy, which is what should happen at the large distance. So, exactly the similar situation, the same variation that we are getting from this particular figure. Now, here we see the stress distribution with reference to the distance in the vertical direction, that is away from the crown portion. So, you see that sigma r variation is this and sigma theta variation is this. So, here you can see that the sigma r at large distance, this sigma by Sy becomes equal to 1, and at a large distance your sigma theta becomes equal to 0. Here this is the 0 axis. So, when we go to the large distance, this value becomes equal to 0. So, this is how we can have the elastic stress distribution around the circular tunnel. So, right now we took at an axis theta to be equal to 0, and this is theta for pi by 2. What about its circumference? How this is going to behave? So, let us take a look. So, here I have tried to plot the variation of these stresses along the circumference. Kindly note that we are only considering right now the uniaxial state of stress with Sx to be equal to 0 and Sy non-zero. So, that is what has been shown here. Now, how this has been plotted, you see that theta equal to 0. So, this is kind of your x direction and y direction. So, theta equal to 0 will correspond to this. So, this has been mapped in this particular manner to this value, and this is theta by Sy. So, what did we get in case of the uniaxial state of stress at theta equal to 0? It was 3. So, that is what that you are getting here. So, these are the values of basically theta. So, similarly, when theta is equal to 90, you are getting minus 1. So, likewise, let us take this theta maybe say 30 degree. So, see, if you just substitute in the expression, so you have this sigma theta as half s y 1 plus a square upon r square plus half s y 1 plus 3 a to the power 4 upon r to the power 4 into cos of 2 theta. So, just substitute theta to be equal to 30 degree and you will see that sigma theta will work out to be equal to 2 times sy for theta equal to 30 degree. Similarly, maybe you can consider theta to be equal to 60. Some typical values I am just taking. So, you see here, just substitute theta equal to 60 degree here. So, you will have here sigma theta as of course, we are considering at the circumference. So, r is equal to a. So, this first term is going to be half sy into 2 and then the next term is going to be half sy into 4 into cos of 120 degree, which is half with a negative sign. So, what does this gives us? So, this is going to be sy and this is also sy. So, with a negative sign, so this becomes equal to 0. So, this is what that we are getting in the variation. So, once we have the various expressions, so for a typical situations, we can determine its variation along maybe theta equal to 0 axis, theta equal to pi by 2 axis and all along the circumference of the circular tunnel. So, this is how we can get the elastic stress distribution all around the circular tunnel. What about the displacements? Now, that we will see in the next class. Thank you very much.